All right, let's jump right in. We're going to talk about an invisible force that, honestly, shapes our entire world. You see it in the incredible flash of a storm, and you see it in the quiet glow of your smartphone screen. We're talking about electric charge. And trust me, by the end of this, you're going to see it absolutely everywhere. I mean, we've all seen its raw, untamed power, right? In a single bolt of lightning, this force unleashes an insane amount of energy. It's this truly awesome and, yeah, kind of terrifying display of what nature can do. But it also shows up in these much smaller, quieter ways. If you've ever rubbed a pen on your sleeve and watched it magically pick up little pieces of paper, well, you've seen the exact same force at play. So what on earth is the connection between a massive lightning strike and a simple little party trick? Well, the answer is something called electric charge. It's a basic, fundamental property of matter, just like mass is. You can't see it, you can't hold it, but it pretty much governs how a huge part of our universe works. You know, the first people to really notice it and write it down were the ancient Greeks, more than 2,000 years ago. They saw that when they rubbed a piece of amber, it would suddenly attract light things, like feathers or hair. And the Greek word for amber, it's electron. Sound familiar? That's exactly where we get the word electricity. So to really get a handle on this force, we have to understand a super important rule. It turns out electric charge isn't just one thing. It actually has two distinct faces, and the way they interact is everything. Simple experiments show this perfectly. So if you take two glass rods, give them the same kind of charge by rubbing them with silk, and then bring them close, they actually push each other away. And the same thing happens if you do it with two plastic rods rubbed with fur. They also repel. But here's where it gets really interesting. Look what happens when you mix it up. You bring that charged glass rod near the charged plastic one, and they don't push away. Nope. They pull towards each other. They attract. And this leads us to this simple, beautiful, universal rule that's behind all of it. Objects with the same type of charge push each other away. They repel. But objects with opposite charges pull each other together. They attract. This one idea, it's the key to everything else. So the big question is, where does this charge actually come from? I mean, when we rub that pen on our sleeve, what is physically happening on a scale that's way too small for us to see? Well, it all comes down to the atom. See, atoms have a positive part, the nucleus, that's kind of locked in place, and surrounding it are these tiny negative particles called electrons that can actually move around. So when you rub two things together, you're not creating charge out of thin air. You're just scraping some of those loose electrons off of one object and transferring them to the other. The object that gains the extra electrons becomes negatively charged, and the one that lost them is left with a positive charge. Simple as that. And what's really fascinating is that you can even move these charges around without ever touching anything. It's a process called induction. Just by bringing a charged rod near a neutral sphere, you can cause the charges inside to separate. Then, if you give them an escape route, like touching it with your finger, some of those charges will flee. You take your finger away, then the rod away, and voila, the sphere is left with a net charge. It's like influencing a crowd from a distance. Okay, so we know there are two kinds of charge, and we know they attract or repel. But how strong is that push or pull? How can we actually put a number on this invisible force? Well, you've probably felt this yourself. In experiments like this one, the attraction is really strong when the charged pen is close to the foil. But as you pull it away, you can see the force gets weaker and weaker. So we know the force has to depend on distance. So back in the 1780s, this brilliant physicist named Charles Coulomb measured this relationship with incredible accuracy. He gave us this equation, which we now call Coulomb's law. Basically, it says the force gets stronger with more charge, but, and this is the key part, it drops off with the square of the distance. So if you double the distance, the force doesn't get 2 times weaker, it gets 4 times weaker. And just how strong is this force? A Coulomb is our standard unit for charge, and it turns out it's a huge amount of charge. To give you some perspective, the force between two single coulombs just a meter apart is 9 billion newtons. The source material puts it this way. That's like the weight of a giant supertanker. That's just mind-blowing. Now, a force that depends on the square of the distance, that might ring a bell. It behaves just like another fundamental force of nature, gravity. But even though they follow a similar rule, they are profoundly, profoundly different. Let's just put them head to head. You can see the formulas look almost identical, But gravity depends on mass, while the electric force depends on charge. But here's the real kicker. Gravity only ever pulls things together. It's always attractive. But the electric force, as we've seen, can both attract and repel. It's got two moves. And that brings us to the absolutely staggering difference in their strength. The electric force pushing two electrons apart is 10 to the power of 42 times stronger than the gravitational force pulling them together. That's a 1 with 42 zeros after it. On the atomic scale, the electric force isn't just stronger than gravity. It's unimaginably, ridiculously more powerful. Okay, so let's bring this all back home. We started with a little spark of static and a giant bolt of lightning. Why does understanding all this detail about an invisible force matter so much to us today? It matters because our entire modern world is built on controlling it. We've learned how to make electrons flow through materials we call conductors. That's the copper in your charging cables and power lines. And we've learned how to stop them cold with materials called insulators, like those ceramic discs on high-voltage towers. This simple control, making charge go where we want it to, that's the foundation of literally all of our technology. When you think about it, from the ancient Greeks rubbing amber to the incredibly complex circuits running inside your phone, our journey to understand and master electric charge has completely reshaped our world. And it all started by noticing a simple, invisible attraction. It really makes you wonder, doesn't it? What's the next spark of genius going to be? What other invisible forces are just waiting for us to find them?